Okay. So, we have been discussing with time varying voltage applied across an inductor. For example, let me do another exercise. For example, just to highlight what I told you, I have connected across an inductor a voltage like this. This V t could be anything L, but with this polarity, and I will assume the current like this I, and I is expected to be time varying because it will be a differential equation L d I dt. This is plus minus L d I dt, as you can easily see it is equal to supply voltage V t. Now, suppose I say that I 0 minus was equal to 0. When I connected this V t across L, previous to that there was no current in the inductor. If that be the case, what will be the nature of the current if I apply say a voltage like this? This is T, this is I t. Therefore, suppose this is 0, this is T by 2, this is suppose T. I apply a square voltage of magnitude V and this is also minus V. Let us see what can we just tell. Yes, we can tell. See, between 0 to T by 2 you have applied a constant voltage. I am not going to solve this circuit. We know that I t between 0 to T by 2, the current of the inductor will be how much? V by L into T straight, because V is constant level voltage. It will increase in the form of a straight line. And where from it will start? Initial current was 0, so it will start from 0. So, it will start from 0 and it was increasing like this, like a straight line. So, what is the maximum value at t equal to T by 2? It will be V by L into T by 2, put that value of T. Now, you see this axis is current. Voltage applied across the inductor, that is with this plus this minus, it is indeed positive and current was increasing, is not. So, during this time this is what is happening, and I at t equal to T by 2 will be equal to V by L into T by 2 at this instant, fine. Now, for t greater than T by 2 and less than T you have applied a negative voltage. So, current must rise. So, at this point T equal to T by 2, inductor had some initial current of this magnitude, and you have done as if some switching, so that it has become a negative voltage. But current cannot change instantaneously, it will maintain this current at T equal to T by 2 plus as well, a small here from only it will start. But applied voltage is negative, and d I dt, as I was trying to tell you earlier, it depends upon V t by L. But V t is negative, so current must have a negative slope. So, current will have a negative slope, and at t equal to T it will be once again current in the inductor will be 0. Why it will be 0 at t equal to t by 2? Okay, mathematically you do, you will get it. Okay. Write down the expression of this, put t equal to t, this I leave it as an exercise to you. Rather, I will tell you physically what is happening. See, to establish this much current V by L into t by 2, how much volt second you have spent? This much volt second. V dt integral, mind you, I V dt 1 by L, L is constant. So, this much volt second I have spent. In this case it was simple, V into t by 2. So, volt second spent was V t by 2 to establish a current from 0 to V by L into t by 2, this level. Therefore, to make the current back to 0, you have to apply a negative volt second of same amount. And you see, this is also t by 2, the volt second associated with this just matches, and therefore, current value once again will become 0, back to 0. So, if you apply a positive volt second across an inductor, current will go on rising, and if you apply negative voltage, current will start decreasing. d I dt is negative here, d I dt is positive. For example, just to complete this discussion, I ask you that look here, I will draw in a this portion I will delete. Suppose you see that I have suppose applied a voltage which is equal to, I will put some number now 0 to 5 seconds, this is t and this is say 10 volt. L is equal to say 2 Henry, okay. And I will this negative half I will apply a voltage of minus 5 volt. This is 5 seconds, mind you. I will apply a minus 5 volt voltage. Okay. And I will apply it for say and this is suppose 5, this is suppose 15, 5 into this interval, this is suppose 15 seconds. Now, you see, and you started the game with initial current 0 in the inductor. Let us try to draw the current waveform. So, here to here it will increase like a straight line whose value will be V by L, that is 10 by 2 into 5, 25 ampere, is it? It will reach 25 ampere, and I am assuming inductor is capable of carrying that 25 ampere current. So, I have applied positive voltage, current linearly grew up from 0 to 25 ampere. Now, beyond 5 to this 15 second, that is this interval is 10 second. You have applied a negative voltage. Therefore, inductor current has to decrease. because V has become negative, d I dt will decrease. Now, I will not do any mathematics, you can write down and get it, but what I am telling, during this positive cycle of the voltage applied, positive half, you have spent how much volt second? 50 volt second. In the negative voltage when you have applied, how much volt second you have applied? Once again 50, but in the negative sense. Therefore, current will once again become 0 at this point. See, the applied volt second that integral V dt depends upon what kind of voltage waveform you have applied. And no matter, for example, this 50 volt second could be achieved by some positive voltage waveform like this also. But I am telling, what I am trying to tell, that at t equal to 5 second, if you have applied 50 volt second, accumulated volt second, this current will be 25 ampere. Positive volt second I have applied. Similarly, negative volt second you have applied like this. So, this is how things you must understand, that is volt second applied like that, and I leave it to you also think about this. Later I will discuss. Suppose you have applied for this problem, for the same problem you have applied a 5 second here and you have applied 10 volt, and in the negative half it is once again minus 10 volt, but only for 2 seconds. This is t equal to 7 seconds. I will tell physically only how much positive volt second you have applied, 50. So, it will increase current linearly up to this point. And reach some value which I can calculate. If I know L etcetera, I will be able to calculate. So, you have spent 50 volt second to establish this much current from 0 initial current, it will go like this. In the negative half, how many volt second you have applied? There you applied 10 into 5, 50 volt second you have applied, but this interval is 2 second, because 7 minus 5, this point is 5. How much volt second you have applied? Minus 20. Therefore, current after this will not reach 0 value, but after that you have not applied any voltage. What does that mean? The inductor voltage between these 2 points is 0. That means, the inductor is shorted beyond t equal to say 7 seconds. So, inductor current will circulate like this. So, this is 5 seconds and this is 2 seconds, and if the voltage pulse is like this, it was 0 earlier, then beyond t equal to 7 seconds it is once again 0, then the current will be, it will reach some value, it will come back, and I ask myself, I applied some positive volt second, then I did not apply the same amount of negative volt second. So, current cannot become 0. So, whatever will be the current, that will be maintained in a short circuited inductor beyond t equal to 7 seconds. Got the point? Anyway, think about it. This is so nice, storing inductor and solving this kind of problems. Now, today I will start similarly another energy storing device is capacitance or capacitor. It is a circuit element denoted by C, which is just it is called a dual element in compared to an inductor. It is also an energy storing device. And we know from our school days that voltage across the plate of a capacitor, if you denote it by V with this plus this minus, and this capacitance value is C. If charge on the plate of the capacitor is Q, plus one plate will be plus, other plate will be minus, then with this polarity marking V is equal to Q by C, is not? This is the thing. From our school days we know. Therefore, to have voltage across the plate of the capacitor, you must have charge on the plates, equal charge plus minus on both the plates. Then only it will have some voltage across the terminal. Now, the question is how charge can be put in a capacitor. It can be, charge can be established or can be brought onto the plate of the capacitor if you allow some current to flow, is not? I is ampere, which is nothing but coulomb per second. So, this is coulomb per second. Coulomb per second is the current. Therefore, this is ampere, this is we know. Therefore, to establish some coulomb on the plates, I must pass some current over some time I t. So, Q is nothing but, if you the present charge on the plate of the capacitor will be how much current you have put on the capacitor from minus infinity to t. That will give you the present charge on the plate of the capacitor is equal to present charge on the plates of the capacitor. So, you have to excite the capacitor with a current source. You must feed some current to the plates of the capacitor, and therefore, once Q is obtained, then voltage across the plate of the capacitor will be Q by C, and I will write it as 1 by C minus infinity to t I dt. This is the thing. While analyzing the circuit, we will not go to the extent of Q, because circuit solution means voltage current. We do not go generally up to Q. So, this is the relationship between voltage and current across the plate of a capacitor. So, if I show it in this way, I will say, if you are showing this is the current direction, this is my prerogative, I can choose in any way, but once you choose that, better choose the voltage of this plate and this plate to be minus, and this is the voltage. Therefore, the present value of the voltage across the plate of the capacitor will be Q by C. So, 1 by C, and Q is nothing but minus infinity to t into I dt. This is I, this is V t. Conversely, one can write I t is equal to C dV dt. This is also correct. In fact, we will be using this mode, but to see, you see, can we say capacitor is a memory-less device? Certainly not, because present value of the voltage does not depend on the present value of the current. It also depends upon the previous history of currents that you have fed in from minus infinity, including the present value of the current, because this integration requires the I values to be known from minus infinity up to the current time t, unlike a resistance V is equal to R I. Voltage across the present value of the current is V by R, R is constant. So, present value of the voltage only decides the present value of the current, no previous history is needed. But in case of inductor, we have seen I, L, T, inductor current, it depends upon the previous voltage you have applied. You recall, same equation in different form. So, this is a memory element with the memory, circuit element with memory capacitor. Got the point? So, this is important, the direction of the current, polarity of the voltage and their differential form of relations and integration form of relation, that is the thing. Acha. Then I will do exactly what I did for the inductor. For example, the voltage across this capacitor, I will write it into 3 pieces, like 1 minus C into minus infinity to 0 minus into I dt. So, what is the circuit here? Circuit means here is a capacitor and we are feeding it from a current source, time varying current source. Got the point? I am pumping current, charges are being stored, hence voltage develops across the capacitor. That way, if you think, it will be better. So, 0 to minus. Then next term I will write 1 by C 0 minus to 0 plus I dt, and then I will write 1 over C 0 plus to t. I can always write like this whole integral minus infinity to t can be broken up in this way. And then I will say that this current, whatever this current source is a reasonable current source. It is not, it does not include impulse. IT current source IT does not is not an impulse source. It is a reasonable function, maybe triangular, maybe sinusoidal, what not. So, I has a reasonable good function. For example, of course, of any arbitrary shape. For example, it could be like this. Suppose you feed the capacitor with this current over time, minus infinity to up to this time t. And in the same way, 0 minus is a time here and 0 plus is a time there. And at t equal to 0, I am doing some switching in the circuit. That is what I want to mean. Now, the question is, if you exclude IT will not have any impulse, then this integral has to be 0, because this integral 0 minus to 0 plus, as you make that 0 plus as small as you please, 0 minus as small as you please, this area vanishes. This is nothing but the area under the curve. So, this area will be 0 this integral, and so this is the general expression. Therefore, I will say that what will be the voltage across the capacitors. So, this is the general expression, fine. Put any value of time t equal to 5 second, you will get the voltage across at t equal to 5 second. So, I will now say V at 0 plus. So, what should I do? T will be 0 plus. So, this will have only these two pieces, 1 by C minus infinity to 0 minus I dt plus 1 by C 0 minus to 0 plus I dt. Is not t equal to 0 plus. So, this term will vanish. I have reached 0 plus, I will stop here. Now, the question is, this quantity is how much? If it is not an impulse, it will be 0. The area under this curve, this will be 0. So, you will be left with V 0 plus, and what is this quantity? Minus infinity to 0 minus I dt. V t is minus infinity to t I dt by C. So, this is nothing but V 0 minus, is not. Therefore, I will say that unlike an inductor, voltage across the capacitor plates cannot change instantaneously. It must be a continuous thing. I am presuming that at t equal to 0, I am going to change something in the circuit. I am applying different current to the capacitor or things like that. Therefore, in an inductor capacitive circuit, it is the voltage which will be continuous whenever you do some switching. That is the important thing. Okay. Therefore, we write in language also, so that you remember it. Voltage across the capacitor cannot change instantaneously. It means capacitor voltage VCT, if I write voltage across the capacitor, this VCT, it will never have, it was doing like this, it cannot do like this. A sudden jump cannot happen. T equal to 0 minus some finite minus 5 volt, at t equal to 0 plus 5 volt, I say 2 volt, then plus 5 volt. No, a sharp jump, vertical line will not be present in a capacitor, as sharp rise in current in an inductor will not be present. Therefore, we say that voltage across the plate of the capacitor cannot change instantaneously. Okay. Now, the second thing is that capacitor stores energy. And obviously, it is a energy storing element like inductor, and whenever you would like to retrieve that energy for practical uses. So, how to find out that energy stored in the capacitor? It can be very easily done. Suppose you have a capacitor like this, see, and here you have connected a suppose current flowing through the capacitor is IT, and voltage across the polarity convention must be followed, IT, and this is suppose the voltage across the capacitor is V. So, I t is equal to C dV dt, is it? Current through the capacitor is C dV dt. Let at t equal to 0, that is V 0 minus was 0, there was no voltage across the capacitor. So, V 0 minus is equal to V 0 plus, that is fine, is same as for all practical purposes V 0, voltage at t equal to 0 is this. Now, therefore, if that be the case, then how to calculate the energy stored? So, instantaneous power at any time t will be voltage across the plate of the capacitor into current C dV dt, is not. This is the instantaneous power, and this becomes equal to C V dV dt, instantaneous power. Therefore, power and see the direction of the current and polarity of the voltage is such that it is absorbing power. So, power, instantaneous power absorbed, instantaneous power absorbed is equal to this. Therefore, energy absorbed by the capacitor in time dt, very small time interval dt, will be P t into dt, power into time gives you the energy, that is equal to dW, and this will be equal to C V dV dt into dt. So, dt goes, so this is equal to C V dV. Therefore, the total energy supplied to the capacitor. So, it is now an integration to be done with respect to voltage across the plate of the capacitor. Suppose the voltage across the plate of the capacitor change from 0 volt V equal to 0 volt to V equal to some volt capital V. So, this will be V dV and this will become equal to half C V square. In general, if you know the instantaneous value of the voltage across the plate of the capacitor at any given time t, then at that time the energy stored simply will be half C into that instantaneous voltage square. Therefore, a capacitor is a energy storage device, energy storing device, just like an inductor, and what we have concluded is that voltage across the plate of the capacitor cannot change instantaneously, and voltage will be continuous whenever you do some switching. I stop here, we will continue next time.